Hello. In today's lecture, we will discuss atomic and nuclear physics. It will be our last topic, and this will be the first lecture from this topic. So far, we have discussed classical physics. So, classical physics as I have mentioned in the first lecture, classical physics includes mechanics, so mostly the works by Galileo and Newton. Then thermodynamics. These were the works by, there were a lot of scientists that had impact on thermodynamics. As I remember, there was scientist Boltzmann, Carnot, Maxwell, who was famous for electromagnetism. Some of them I might be missing, but you can, if you're interested, you can look somewhere. So electromagnetism works by Faraday, Maxwell, Hertz, and optics. So these were considered classical physics, and atomic and nuclear physics, or quantum mechanics, all together with Einstein's theory of relativity, special theory of relativity, and general theory of relativity, they are considered to be modern physics. So it means they were developed in the 20th century. So quantum mechanics and Einstein's theory of relativity. So they were developed in 20th century. These all were developed up to 20th century. So quantum mechanics, this means atomic and nuclear physics plus Einstein theory of relativity in 20th century, and this refers to modern physics. So classical physics refers to what we know, to what Newton's laws of gravity, then we can explain the universe, the motion of planets, conservation laws in thermodynamics, electromagnetism, electromagnetic waves, optics, the laws governing the behavior of electromagnetic waves. So this is the optics, and the general idea was that in the end of 19th century, the beginning of 20th century, that all the laws of physics were understood, and everything seemed clear, but then scientists tried to explain atomic phenomena, atoms. So they tried to explain this using classical physics, and principles of classical physics were unable to explain the structure of atom, and the main reason is that atom has nucleus. Nucleus is, we can show it as it is some kind of, let's say, circular nucleus, and nucleus is composed of neutrons. You know, this nucleus is composed of neutrons, has no charge, plus protons has positive charge, and electrons are moving around the nucleus. So electrons, they move in circular orbits around the nucleus, like planets around the sun. And let's say this is electron. It's moving around circular orbit. This is another one electron. And what's happening, because this orbit is circular, so electron has centripetal acceleration. And as you remember, this is the part from mechanics when we were talking about motion, that was not in a straight line, that was in a, let's say, circular or curved line motion. And when objects moves in circle, it has centripetal acceleration. It means that it's the direction of its, we have an object and is moving with v, velocity v. So it's the direction, although this object is moving at constant velocity, constant speed, but direction changes. So its velocity changes, and this velocity changes due to centripetal acceleration. Centripetal acceleration. So as I told you about Maxwell's equations a bit, I mentioned that Maxwell's equations, that there was an equation where means rotational magnetic field, rotor of magnetic field. It is it can be understood as the current density, what refers to current plus some constants, and changing electric field in time. So basically what is saying that magnetic field, this is differential form that you probably don't know because it's, you are only first year. Magnetic field is produced by current. This is current density, current divided by surface area. So by current plus and also it can be, magnetic field can be generated by changing in time electric field. So E field, let's say E, magnetic field, so it would be, magnetic field would be B, yes? So changing in time, so it means that if electron is moving with acceleration, so electron is emitting electromagnetic waves. So if charge is moving with, if charge is moving, so it means that this is current, so charge is moving, but if it's moving with constant speed, no acceleration, so it's just direct current. If electron is moving with constant speed, if acceleration is zero, so it means V is constant, so then what happens, so it produces magnetic field, but magnetic field is like of a bare magnet, so it is not changing, it's constant. But if electron is moving with, so then B seems to be constant. This needs to be solution here, so just you have to believe me this time. So if A is not equal to 0, so V is not constant, so this means that B is changing. B is changing. So if B is changing, then of course it's changing in time, and that changing in time B field can produce electric field. B changing in time can produce electric field, and then electric field can produce magnetic field, and this goes. So electromagnetic wave. So electron moving at acceleration, it can produce electromagnetic wave. So if electron produces electromagnetic wave, so what happens then? It would radiate this electromagnetic wave, and its energy that it has by moving on this orbit. So if it produces electromagnetic wave, then he will radiate all its energy and fall down on nucleus. So this would happen at very rapid time scale, but so existence of atoms would be impossible on the, based on classical physics. So so this doesn't mean that classical physics doesn't work. It means that it has limited range of application. So classical physics was able to put man on the moon, but to explain atomic scale phenomena, we need another theories. So just for atomic scale phenomena, we will have to think of other laws. And the beginning started explaining this started by Einstein. Einstein is famous for relativity. Relativity is a bit different thing, but he started this this way for quantum mechanics, but later in his late years he was somehow against quantum mechanics. He was denying the theory, and he wanted to change it, to make his own theory that would explain all the phenomena by connecting gravitational theories with gravitational theory is in Einstein's Einstein's theory of relativity is more accurate gravitational theory than Newton's. So by combining his gravitational theory, that means theory of relativity, with electromagnetical theory of electromagnetism. He wanted to make some kind of field of science that would be better than quantum mechanics, but he wasn't successful on this. Anyway, he laid the foundation for quantum mechanics, and this was done by photoelectric effect. There was such kind of unexplained phenomenon as photoelectric effect. So if you have a metal plate, there are electrons. As you know, metals are good conductors. There are electrons that are not bound to particular atoms. They're moving freely. So when light of particular wavelength, so this is light, hits the metal surface, so electron absorbs this energy and electron flies away from this metal. So, but it means that, but what was strange that if the color of this light was red, as you remember, red has about 700 nanometers, so it is rather long in the visible, it's rather long compared to other colors. So when the red color doesn't produce these electrons are called photoelectrons because they were generated by light, photo. So red was unable, even if the intensity was increased. Intensity, that means so red was unable even if the exposure duration was increased or intensity was increased of this red light. So it means frequency or wavelength was the same of red light, but exposure duration was increased, intensity was increased. This is joules per second into square meter. Intensity, energy per unit time to some kind of area. We have some kind of area, square meter. In a second we get some kind of light intensity, energy. And green and blue were able to produce electrons, and when electrons were emitted by green light, so electrons were flying with, this had some kind of kinetic energy, this flying electron, in case it had kinetic energy. So if it's flying, yes, it had kinetic energy, but blue color produced electrons having more kinetic energy. So it means that this was flying, it had some kind of velocity v. So this electron was flying with capital V, let's say. So blue color, so because blue color would be some kind of, I'm not here precise, about 450 nanometers. Green color would be around 550 maybe. So this means that they had shorter wavelength, higher frequency, so they were able to produce electrons. So this means that there was red color was unable to produce photoelectrons, even if its exposure duration was increased or intensity was increased. So in classical physics, if you increase intensity or exposure duration, so this electron should have accumulated energy and then left this metal plate. But here green and blue were able to produce photoelectrons. It doesn't matter the exposure duration or intensity. Of course, doesn't matter in some reasonable range, yes? So this means that the influence of wavelength or frequency, because they are related, yes, is crucial in this photo effect. So what did Einstein do? He said when light interacts with matter, here light interacts with matter, so he said that light acts as particle, and this particle he called photon. So he said light can act as particle, as photon, and photons are particles of light, and it is quantum of electromagnetic radiation. So light can be thought as a particle, photon, and photon is a quantum of electromagnetic radiation. So quantum, it means something is quantized. Quantized, it means has discrete amounts. Yes, discrete amounts. Not continuous, but discrete. And photon has energy, so energy photon would be h times f, or it be, because frequency, this is Planck's constant, Planck's constant. Planck's constant is has the units of 6.63 10 to the minus 34 joules times seconds. So this is Planck's constant, this is frequency. So frequency can be related by speed divided by lambda, wavelength. So we can write that hc lambda. So this means that photons having a higher frequency, shorter wavelength, they have more energy, and therefore green and blue lights their photons could produce photoelectron that would go from this metal plate. And here red photons, multiple photons with less energy do not produce photoelectron. They were unable, and this is the energy of photon. And here you see that photon can be thought as particle here, but in classical theory, light is thought as a wave, and here light is thought as flow of particles. So this is what was contradiction with common thinking, general physics, that light can be treated as a particle and can be treated as a wave. But this is true. So this photon's energy, was used for energy to release electron release, plus to give the electron kinetic energy. So photon energy became the work needed. Let's maybe write work needed to release electron and give him kinetic energy. So quantum concept is that in classical physics, energy was thought as to be found in continuous amounts. And now quantum concept is thinking about energy in quantized. Quantum concept thinking about energy in discrete amounts. Quanta. Quantum is singular form, quanta plural form. So discrete amounts, quanta, or in case of light, photons. And now what was general step in, sorry, not general, but the next step in explaining the structure of the atom was that scientists were trying to explain atomic emission spectrum, or spectra in plural form, or spectrum if it's singular. Atomic emission spectrum, let's say. So atoms, excited gas, do emit light, but at very narrow and specific wavelengths. So each element produces unique fingerprint spectrum. For example, hydrogen, it produces, it doesn't matter the wavelength, but just you can find it everywhere, but it means that it produces some kind of narrow wavelength light, and all here would be black. So all here would be black, so it means that this hydrogen produces only this specific nanometers. Of course I don't remember them. It doesn't important because it's important for analytical chemists who are using this for analysis. So what means that hydrogen produces some specific wavelengths emission. It is not that emission that electron is falling on the nucleus. That in that case the spectrum would be continuous, but here it is discrete. So you see discrete. This word discrete here, and spectrum is discrete. So it means that something is making sense. So in trying to explain these things, physicist Niels Bohr, he made the model of atom. So he tried to explain these things, and he proposed atom model, and he made a postulate that postulated means that some kind of assumption that is not proved. Postulate that electrons in atom can only be in certain stationary orbits or states. In these states, they do not radiate electromagnetic waves. And the illustration of this is that we have nucleus and we have let's say orbits of electrons. We can say that we have one electron here, another electron here, another electron here, and so this would be N1, the number of these states, N2 and N3. And it means that these are the states of energy, and if electron is in these orbits, in these states, it doesn't radiate electromagnetic waves. But if somehow this electron makes jump here to this energy state, so this is lowest energy state 1, 2 is higher energy, and 3 is the highest energy. So if the electron goes from this state 3 to state 2, orbit 3 to orbit 2, then what happens? So electron has to lose some energy, so then it emits electromagnetic wave in order to take this state with less energy. So if it goes here, then it emits electromagnetic wave. So this is delta energy, the change of energy that is emitted by electromagnetic wave, and it can be written that it would be delta E would be E final minus E initial, and it would be equal to what? Hc divided by lambda. So the same that Einstein was speaking about. So the spectrum that electron moving from higher energy state to lower energy state produces this kind of electromagnetic waves with this energy, and this spectrum is called emission spectrum because waves are being emitted. So using this model, Bohr was able to explain these, to prognosticate, calculate, so means explain this spectrum of hydrogen atom. But because for him it was easier, because hydrogen atom was having only one electron, so it means that anyway, if it has one electron, so it can move to lower energy states. So it means that this, for example, this in this case, there would be no of these red dots. So you can imagine that there are no red dots, and this would be one electron in hydrogen atom that can go in this kind of state, and two that has less energy, or in this one that has the least energy. So if atoms have more electrons, so here and here would be, so then it would be more difficult to explain, because there are electrostatic repulsion forces, and that where Schrödinger's equation comes in, and other things that it's more difficult. So what we see that in quantum mechanics, like photon can be thought as wave. Photon can be thought as wave and as particles. It means that light can be thought as wave, and particle. So it means that electron is a very small particle, or it can be thought as a wave also. So it means that instead of thinking about electrons moving in orbits around nucleus, we can think about electronic cloud of an electron, where it is like not as particle, not as wave, but just some kind as cloud that has both properties of particle and waves surrounding it. So it means that electron could be thought as a cloud surrounding the nucleus. So it's known as wave particle duality. And wave particle duality. So another thing that comes from this wave particle duality is Heisenberg's uncertainty, difficult word, uncertainty principle. So Heisenberg's uncertainty principle. So in classical physics, position and velocity of an object could be measured simultaneously with as much accuracy as the device of measurement allows. But so position and velocity. So position and velocity we could measure, because we were having big objects, huge objects. Okay, here we have small object, very small, uncomparably small to this. So we have small objects. So what does it mean? It means that when we go down to atomic level, it becomes very important that measurements themselves disturb the systems we are trying to measure. So if we hit electron by light, so then electron is disturbed, is moved. So in classical physics we deal with large objects. So here velocity and position is not disturbed by measurement process. So what does it mean we want to locate the electron or measure its velocity or any object? We need to, let's say, to see this object, we need to emit so we need to look at it. So to look at it means to shine a light on it. So shining a light on it and see how the light scatters back to our eyes. Yes? To our eyes. So light shines on it and scatters back to our eyes. So imagine that electron, very small particle, is moving somewhere. It is moving here. We shine a light on it. So it is hit by a photon. And as in previous example, as photons were hitting electrons and electron was flying away from this metal. So here, when we hit with photon this electron, what does electron do? It changes, it starts moving, changes direction. So we hit, it was moving here, we hit here, so electron starts moving here and it moves. So it means that we have disturbed the electron, we change its direction, we change its velocity, and we change its location. So it means that it is, with this photon, we changed the behavior of electron, its position and velocity. So it means that measurement itself produces changes the quantity that we want to measure. This means position or velocity. So this means that if we lower the light intensity, the photon's energy, then we make smaller alterations, but nevertheless we cannot avoid these alterations, and therefore this uncertainty principle says that it is impossible to precisely measure the position and velocity of electron. So this is this is uncertainty principle, that impossible to measure position and velocity of electrons simultaneously. So this is Heisenberg's uncertainty principle. So thinking about the electromagnetic waves as photons, so what kind of electromagnetic waves do we know? We know according to frequency, yes. We know radio waves, we know microwaves, we know infrared light, we know light, visible light, yes. We know ultraviolet light, we know X-ray, we know gamma. So these all can be thought as radio and TV waves. So these all can be thought as photons, flow of photons. So X-rays, how X-rays have lambda of X-ray, wavelength of X-ray is 0.1 nanometers, so it's very small as compared to light in hundreds of nanometers. Here it is decimal part of a nanometer, so X-rays are produced in produced in this way. So we have tungsten filament. Tungsten filament is heated, so it means that current is flowing through this filament, and it is heated, so this means that electrons in this filament have energy. So then a high voltage is applied this is high voltage, and this would be some kind of conductor, metal. This is called anode, and this is called cathode. And when electrons here are heated, they have energy, and when high voltage is applied, so here it is vacuum. This is vacuum here. And when electrons have high energy, so they want to leave this tungsten filament, and when high voltage is applied, the electrons they move to this anode, they strike it. They are moving at very high speeds. So if they are moving at very high speeds, so it means that they have kinetic energy, very high kinetic energy, and the part when they hit this anode, they suddenly stop, and the part of this kinetic energy is turned to X-ray. And X-ray, as you know, they can penetrate to skin and tissue, but cannot penetrate through bone, so they are used for diagnostic imaging. So, but because they can penetrate through skin and bone, they are dangerous they can cause mutations, alterations in cells, cancer, and all the other things. So that's why extreme caution must be taken when dealing with these things, because when we get to high frequencies, means short wavelengths, then it is danger, and gamma, it is terrible thing to work with unless extreme caution is taken. So another thing that I want to talk about is laser. What is laser? We know that laser is something advanced. So laser, so if we have electron in the atom, an electron is here, let's begin maybe with let's say it is this kind of situation. So if this electron is here, this is energy 1. Energy 1 is less than energy 2. Energy 1 is less than energy 2. So, and then light comes to this electron. So light comes to this electron. This is light. This is maybe not a, so light comes to this electron. So this electron, what does it do? It moves. It moves from this state, from E1 state. It moves up here to E2 state. It absorbs energy, so it moves to E2 state here. Moves here. This is E1. And while being here, this is phase 1, this is phase 2. While being here, after some time, it goes back to E1 state. It goes back to this E1 state. So it goes back to this E1 state by emitting this light. That was coming. This light was coming and he is emitting this light. So he went down to this E1 state. So electron absorb light. Electron absorb light. Electron was here. In one picture, if I'm to, electron was here. It absorbed light. He went up here, and then after some time he went back down here and emitted this light. So this is what I was trying to illustrate in stages. But what happens if electron, so this is spontaneous emission. Spontaneous emission. So, but what happens if electron is was in this E1 state. This is E1, this is E2, so this is E1, this is E2. And was in this E1 state, the light came here, so he jumped up, absorbed, so he went here, he absorbed this light, and what happens if another light hits this electron? So then he is forced to go, it seems that he is forced to go back here. And what does he do? So he, in this state, he absorbed this light. So he used this energy of light to go this delta E from E2 to E1 to change his state from E1 to E2. He used this energy of light. So here he has this energy of light. Then suddenly another light comes in, and this electron absorbs this energy. So he wants to jump somewhere. He wants to jump to somewhere up, but if there's nowhere to go up, if there was, he would go, but if there is no place, then he goes down, but here he has to emit all the light that he has absorbed. So this electron emits both photons here. And it seems that if he emits these photons like this, so these are called, they have the same color, they are identically the same, they are polarized, and they have the same color, so it means that they are coherent. So if there are a lot of atoms like this, so all like this produced light rays would be coherent. In this case, here it is one light, one ray of light, one photon, let's say, one. And if there are a lot of atoms, so this light would be incoherent in non-polarized light and in different colors. So in this case, it is stimulated emission. So in stimulated emission, we obtain color of the same light of the same color and single wavelength. So it is polarized light, and if there is also more electrons in E2 state, then this light is amplified. So it means that we have, if there are more electrons in this E2 state, so any ray that is coming here, so one produces, if the material is arranged in the way that there are more electrons here, so one light ray comes, this electron jumps here, and he emits what? Emits this difference and emits this light that made him jump, yes? Absorb. So here we also get amplification if we choose the material where there are more E2 state electrons. So it means that we have in this stimulated emission, by taking the particular material, we can arrange the thing that we get coherent light and we get amplification of light. So this means that we have and this is laser, basically. This is laser, this is the principle of laser. So one particular wavelength, as you know, it can be any wavelength, red, green, red probably the most common, and so it means single wavelength. Another thing that is very popular these days is for diagnostic imaging is magnetic resonance imaging, MRI. So I'm not going into detail to this because it's too complicated for you. I just want to tell you that in water molecules, we have a lot of water molecules in all our body, and the water molecules have these two hydrogens. So each this hydrogen can be referred as it has magnetic properties. This hydrogen has magnetic properties, and when positioned in external magnetic field, these hydrogens are oriented in particular wave, and when they are oriented, they can also be their resonance of magnetic properties. So it means that their magnetic properties are amplified by radio waves. So because different tissues have different properties, so that's why we can use these manipulations of radio waves and magnetic field to get the images of the body. And this is also based on the principles of quantum mechanics in the deeper level. So this is here basically what I wanted to tell you about in the first lecture on quantum mechanics and atom physics, and later we will be dealing with, in the last lecture we'll be dealing a bit more about this thing. So thank you.